All right, continuing in Chapter 2, Section 1, Basics of Functions and Their Graphs. We're going to continue looking at domain and range, but this time instead of looking at domain and range from a set of ordered pairs or a relation, we're going to be looking at a domain and range from a graph. All right, so for example, like if we look at some of these graphs over here, like what would be the domain values for this graph, which means what are all the x coordinates of every point that's contained on this graph? And if you use the roster method, meaning something like what was on the first page, okay, if you tried to use what we call the roster method, just listing the x values and the y values that make up the domain and range, you'd be here forever. It's not possible. I couldn't possibly write down all the x coordinates of every point that's contained on that graph. It'd be unrealistic. So when we look at domain and range from a graph and we don't have a set of ordered pairs, we don't want to list them. We want to describe. We want a description of what are all the domain values, x values, and what are all the y values of these points on this graph. So we're going to describe that. So the way we describe it is, in this case, not the roster method, which lists all the x and y values. We're going to either use set builder notation or we're going to use interval notation. Both of these notations are used to describe a set of x values without having to list all those x values, which of course would be impossible. All right, so what we need to do is we need to first of all find out what does set builder notation look like, and then what does interval notation look like. So set builder notation doesn't list the elements of a set, and we read set builder notation as the set of all x values such that x blah, 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 fits this description on our graph. When we're talking about range values, we're going to use y. We would say the set of all y values such that y blah, blah, blah. All right, so looking down here at some set builder notation, let's see if we can kind of interpret this set builder notation. So when you look at this first description here of x values on a graph, notice the braces on either end, the beginning and the end. That just is a nice way to kind of combine this notation. It's not necessary, not really, but it's good to have, good practice to have those braces. All right, let's come back up here. It says the set of all x values such that x is blah, 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 fits some description. So the way you read this is you'd say the set of all x values, that's how this is read, such that is this vertical bar, such that those x values of points on the graph have to be, this is a greater than symbol, those x values have to be greater than 3. So whatever graph we're talking about right here, we're just kind of we're learning about this notation. I don't have a picture of this graph, but let's say that on this graph, the x values of points on that graph are greater than, not equal to 3, but just greater than 3. So like 3, 3.5, 3.7, all the way up to positive infinity is what we call it. All right, so a way to kind of show what that looks like on a number line is this. Let's say this is my x number line. All right, I want x values that are greater than 3. So anywhere you want, just put 3 on here. Now above 3, I don't want to include 3 because I don't have this little line underneath the greater than symbol that indicates or equal to. So if x values are greater than 3, I'm going to put an open circle. So an open circle means I'm going to exclude 3, but then off of that open circle, I'm just going to kind of draw this line and say anywhere to the right of 3, okay, then all those x values would be points on that graph. So using set builder notation, all x such that x is greater than 3, it would look like this when graphed on a number line. Well, this is going to help us understand interval notation. For interval notation, we don't use these braces. We use either parentheses or we use brackets. These are brackets here. So an open interval, if you use any of these parentheses, whether it's the left parentheses or the right parentheses, indicates that that x value, that number, is not included in our domain or our range. The bracket indicates that we can include that x value. All right, so back here, so we've got set builder notation. This is what it looks like graph. So we're going to use parentheses and brackets or a combination of those. So what we do is we use a parenthesis, and then we say we start at x of 3, but not including 3, comma, that means you go up to infinity, because that's what this arrow is indicating, that x values are getting bigger and bigger and bigger. We're going to positive infinity. It's read as x values begin after 3 and increase to infinity. So it's just a personal preference. Do you want to use set builder notation or do you want to use interval notation? As long as we understand the two notations that represent the same collection of x values, we're good to go. All right, just what if, now done with that, but what if this was x greater than or equal, that little line means or equal to 3. The adjustment would be a closed circle above 3, and the adjustment on interval notation would be that we would have a bracket, not parenthesis, right here. So x values begin at 3 and increase to infinity. So it's kind of important to know, the different notation and what the indication is. Okay, these are just examples of understanding set builder notation and interval notation. So let's look at our next example. This is read as all x such that those x values have to be numbers less than 3. So if I draw a number line, put 3 on here again, less than, not, I don't see a line, so I put an open circle. Now, which direction are numbers going to be less than 3? Well, it'd be this direction. So how do I convert this number line to interval notation using either parentheses or brackets, a combination of both, and some infinities? Well, we always report our answers from smallest to greatest. Always write the interval values smallest to largest. So think about your pencil. You're coming up from negative numbers, very small, up to, you would stop at 3 and not include 3. So that's why we use a parenthesis. We start at negative infinity and we go up to, comma, 3, but not including 3. And just to kind of say this on the side note, anytime you use an infinity, you will never put a bracket on that side of the infinity. You never use a bracket near the infinity, whether it's positive or negative, because the bracket means it kind of stops and infinity doesn't stop. So infinity always uses parentheses. And if you wanted to write that over here, infinity always uses parentheses, that might be a good idea. Okay, let's look at another example. This is read as all x such that x is greater than or equal to 5. So think about the set of numbers that are 5 or higher. If you graphed it, here's your 5. Above 5, I'd put a closed circle because of the little line, and numbers greater than 5 would go this way. How do you convert this into interval notation? Well, I start at 5, so I'm going to use a bracket to include the 5, and I'm going to go up to infinity. So x can be equal to 5. Always use open intervals for the infinities. All right, let's look at set builder notation here. All x such that x is less than or equal to 5. Okay, same thing, but now your arrow is going to go to the left. So I kind of look at my eyes, kind of focus on 5. I'm going to put 5 here, less than or equal to 5. I go this way. So how do I transfer this into interval notation? Well, I start at negative infinity, use a bracket, comma, up to 5, and stop at 5, including it, so I use a bracket. All right, let's look at this next one. It's a little bit different. All x such that, and then I want to start with x. Well, notice that x falls between 3 and 5. X is, when you kind of look at it this way and read from right to left, x is greater than or equal to 3, but x is less than or equal to 5. So x is between 3 and 5. So what does that look like on a number line? Well, now you have two values to put on your number line. 3 comes before 5. I see a little line here, which means or equal to. X is greater than or equal to 3, so closed circle. Remember, closed circle means include. Open circle means not include. There'd be no line here. And then 5, and then I want my x values to be in between 3 and 5. So what does that look like in interval notation? Well, it says the set of x values that include 3 and go up to 5, including 5. And here's the description of that. Okay, let's look at a different case of set builder notation and what it looks like in interval notation. All x such that x is less than or equal to negative 2, or x has got to be a number that's bigger than or equal to 3. There's not a lot of room here. There's not a lot of room here to show that graph, so I'm going to come over here. All right, so let me come back. All x such that x is less than or equal to -2. So we've got -2 or equal to, closed circle, less than goes this way. Or a number x that you can choose that's 3 or greater than or equal to 3. So this graph looks a little bit different because I kind of have two pieces of it, unlike what I had previous. How do I transfer this into interval notation? Well, start from -infinity up to -2. So -infinity up to -2. This union just indicates we have another set of values I have to describe over here. Then there's a gap between x equals -2 and x equals 3. So union, I start again at +3, include 3, and go up to infinity. And one more case here. All x such that x is a real number. If you were to graph that, here's my number line. Notice that I don't have a specific value of x. It's just saying that x can be anything on this number line. So how do you report that in interval notation? Well, it's -infinity up to +infinity. All right, hopefully your comfort level is okay with knowing about set builder notation and interval notation. If it's not, I do have another set of practice problems. It's included on Blackboard. It looks something like this. And so if you want to practice these additional 4 problems and writing the solution set or writing what these graphs represent in set builder and interval notation, you might want to work through this, and the key will be posted. I also will create another short video because this is the only lesson of these 4 problems, and I'll attach that, okay, in the same kind of week's lesson. So if you find that, man, I just need some more practice with this, well then consult, that other worksheet and that video, and hopefully that will give you the extra review that you need. All right, so let's move on now. Okay, we've talked about set builder and interval notation. Now let's talk about finding domain and range from a graph. So we can use either of those 2 notations to describe the domain and range, since we don't have a relation that kind of lists the ordered pairs, and we can't use the roster method. We'd still be here all day for the rest, we'd be here for the rest of our lives trying to come up with a list of x values that are points on this graph. All right, so domain and range from a graph. Okay, so I'm looking at this grid. I can see that the graph here starts in an open circle. It's a kind of linear, it's a line, it comes down, and this graph ends in another open circle down here. So what's the domain of this graph in interval notation? Well, for me, I just kind of, if I'm looking at the domain, I take my pencil and I put it vertically, and I move from the far left to the far right, and I think about, okay, at what x value am I first intersecting this graph? Well, when you get to this open circle right here, if I think about bringing this open circle down to the x-axis and reading it, to the x-axis, I can see that this graph begins at -3, but it doesn't include x equals -3 because that's an open circle. So I come over here and I put a parenthesis, comma, up through. So where do my x values go to? So I use my pencil and I go, okay, I'm intersecting the graph still. Good, good, good. I better stop here at this x value because the graph's not found over here. So stop right here at x equals. So think about the last point on this graph that's not included, bring it up to the x-axis and read that x value. So this graph stops at 6. It's an open circle, so no bracket, just a parentheses. So using interval notation, the x values of points that are on this graph, the x's have to fall between x equals -3 and x equals 6. Some would say kind of collapse this graph, bring it to the x-axis. So if you're above the x-axis, bring all this graph down here. If you're below the x-axis, bring that part of the graph up there. So that's kind of a way people kind of look at domain. All right, what's the set builder notation that represents the set of x values that are all points on this graph? Well, it would be brace. We're talking domains, we use x, all x, such that now x has to fall between these 2 x values. So x is, when you read from right to left, x is greater than -3, and then x is less than 6. End with a brace. I don't need the little lines here because I don't have closed circles. Now let's talk about the range. Now the range are the y values. Remember, domain is x, range is y. So instead of finding the range by going across the graph this way, I'm actually going to start from, think about the vertical axis here. I'm going to start from low y values going up to high y values. But I'm going to turn my pencil horizontally now. When do I start with my pencil intersecting the graph and touching the graph? Well, the first time I'm going to touch the graph, and not really, but kind of get me started, is right here at that point. So let me come across to the vertical axis, come slide over here. Let's read this y value of -1. So it looks like the graph starts at y equals -1, but doesn't include -1. Now keep your pencil going upward. I still have y coordinates within this kind of range here. When do I stop being on the graph? Well, as I get up here to y equals 5, if I read over here to y equals 5, I stop at 5, but I don't include 5. I have 2 open circles. So this describes all the y values of points that would be listed on this graph. So interval notation is all y's such that y is between, it's greater than -1, but less than 5. And again, we have open circles, so that's why I'm not having the little lines here, nor am I having brackets on the interval notation. All right, domain and range is typically a difficult concept for students, and so if you're kind of struggling, we just need more practice, understandably. All right, and if you need to, like, YouTube a video about domain and range, kind of see what their words are, that might help. All right, we're moving down here. Let's look at these graphs that we have here. Let's continue looking at domain and range. Okay, and just for the sake of labeling, I'm going to call this f of x. I'm going to call this the g of x graph, give it a different name. These are functions, okay? I can even use g to represent a function instead of just f. It's just kind of common practice to use f of x. But if we're looking at a bunch of different graphs, sometimes it's good to give the graphs different names. So, and this is h of x, where this is also a function. Again, we don't have to use f every time. It's just the notation with the parentheses that suggests that these are functions. Okay, so I had a label down here. I'm going to move that, and I'm not going to call this the graph of g. All right, let's find the domain and range from the graphs. Okay, and we're going to use interval notation. That in upper level math classes, that's usually the go-to method for reporting collections or a set of values is interval notation. All right, so look at graph F. What's the domain? Well, it looks different than this graph right here because I got arrows suggesting it continues. So if I'm going to talk about the domain, I'm going to put my pencil vertically. And if this graph were to extend offward, it's rising. Okay, it certainly is. Okay, if my pencil is here, eventually if I were to draw this graph extending, I'm going to intersect the graph way up here. So it looks like negative infinity, okay, way over here to the left. No matter where I'm at, my pencil would intersect the graph if I had enough space. So from negative infinity all the way over to, and then even though my pencil is off the graph suggests that it would continue, I would always intersect it. So this is a well-behaved continuous graph. There's no breaks, no stops. So the domain is actually all real numbers. So with domain being all real numbers in interval notation, we say, oh, all the x values of points on this graph could be any x value at all, a negative to a positive. All right, so I'm going to go across and do all the domains for these functions, then I'll come back and do the ranges. Let's look at the g graph. All right, the arrow suggests the graph continues without stopping. So no matter where you place your pencil, from far left to far right, I'm always going to be intersecting the graph of this function. So that means I have x values on all real numbers. Let's look at the h graph. So for the h graph, again, there's an arrow here, but notice that the graph comes up here, turns around, and stops in this open circle. So far left, So even if the graph extended, I'd always be hitting the graph. So these would be x coordinates. So I'm going all the way across, but right here is where the graph ends. So when you look at this open circle and you kind of look down vertically, okay, where does this graph stop? What x coordinates? Well, there's no part of the graph when x is 2 or 3 or any number in between. So I'm going to come up from negative infinity, and I'm going to stop at the x coordinate of 1. I see an open circle, so I better report parentheses for non-inclusion. All right, let's look at range. So instead of going across this way with your pencil, you're going to start from low y and move up to positive y's. So when's the first time this pencil's going to intersect this graph? Well, not down here at these y values of -4, -5. I don't intersect this graph. The lowest y value of a point on this graph would be found at -3. Now that's going to be a filled in circle. So I want to include -3, comma, up through. Well, as I continue upward, all these points on this graph, okay, would contain every y value. So if I'm standing up here at y equals 4, if I look across, yep, that point has a y value of 4, that point has a y value of 4, and the arrow suggests that the graph just continues, so up to positive infinity. Let's look at the range for G. All right, start from low y, move to positive y. Okay, now remember the arrow suggests the graph continues, so this graph could be found way down here. I'm always intersecting the graph with my pencil. I always hit the graph. And no matter how high I go, if the graph continues, I'm going to continue to hit it. So the range, the y values of points on that graph would be any y. A linear function's domain and range are always all real numbers. All right, let's look at h. Okay, so the arrow suggests the graph's down here. So I'm still intersecting the graph. But I can't go any higher than y equals 4 because at y equals 5, there's no graph there. So I would say my range goes from negative infinity up to and including, there's no open circle, 4. So I'm going to put a bracket around there. Again, if you're comfortable, great. If not, maybe, look for a video that describes, domain and range. Mr. Khan does a good job on Khan Academy as well. All right, now we have a few remaining ideas to talk about for basics of functions and their graphs. So let's talk about x-intercepts and y-intercepts. So an x-intercept, kind of think about that word, x-intercept. I'm intercepting the x-axis. Those would be the points. It could be one, could be none, could be multiple. It's the points where the graph crosses the x-axis. The value of x when y is 0. If we're crossing the x-axis and we're on the x-axis, this y value is 0. So it's a point that's listed as whatever that x-coordinate is, comma 0. Okay, something to think about, because this will come up later, is that x-intercepts are synonymous with, we might say, roots. If you're asked to find the roots, they're just saying find the x-intercepts. And also the zeros of a function, meaning the y-coordinates are 0. So these 3 words right here, they're going to be thrown at you, and I don't want you to think that they mean something different. These 3 words mean the same idea. All right, so let's look at graph 1, or the f of x graph. Do we have any x-intercepts? Well, I stand on the x-axis, and I start far left, I start moving to the right. Yep, the graph has an x-intercept here, and the graph has an x-intercept here. So in this case, I have 2 ordered pairs that I want to report. So on graph 1, I have an x-intercept at the point -2, 0. Notice the y's are 0, just like here. And I have the ordered pair 2, 0. So these 2 locations. And just a reminder that this is ordered pair notation. I just put an arrow here. Remember, we could write that in function notation as f of -2 equals 0. This can be written as f of 2, it's my input value, and my output value is 0. All x-intercepts share the y-coordinate of 0. That's what's happening here. I just noticed something. The x-intercept, the points where the graph crosses, or could be, or touches. It doesn't have to actually cross to be an x-intercept, it could touch. All right, let's look at graph 2, the G graph. Okay, do I have any x-intercepts? Yep, I only have one right here. What's that ordered pair? 0, 0. And what's the function notation? Well, I'm not going to use f because the name of my graph is G, so I would just put G of 0. When x is 0, my y is 0. All right, and then you guys try this one. Graph of 3, x-intercepts. Yep, I do have one. Okay, and just down below, I'm going to put the function notation. Notice this is the h graph, so h of -2 is equal to 0. I kind of prefer the function notation just because it tells me what graph I'm working on. Ordered pairs doesn't really describe that I'm working on the h graph, but this is more revealing. Okay. All right, what's a y-intercept? Well, thank goodness we only have one name for that, y-intercept. Not like x-intercepts could be called these. Y-intercepts is just where the graph crosses the y-axis. It's the value of y when x is 0. So when x is 0, what's the y value? So let's look at graph 1. Okay, the y-axis. We're going to look at, do I have a crossing with the y-axis? Yes, I do. It's right here. What's that ordered pair? Well, it has to start out as 0, comma, and the y value of the crossing, if you read it from the y-axis, is -3. Can I write this ordered pair in function notation? Yep, I'm working with the f graph. So the input is 0. When x is 0, the y is -3. So you try these two, and then come back and see how you did. I do have a y-intercept here. It's the same as my x-intercept, and it is at the origin. And so I would call this g of 0 equals 0. Do you have to do both these? No, I just want to kind of front load. So in case we see this notation in a future video, we would make a connection that it means a point on the graph. Okay, do I have a y-intercept here? Yes, I do. It's right here. It's when x is 0. I'm not moving, but I'm left or right. I'm just moving vertically. 0, 4. And the function notation would be h of 0 equals 4. All right, and the last idea in this lesson, this chapter, section 1 and chapter 2, is evaluating functions from a graph. All right, we've already evaluated functions. We did that on the first page. We evaluated functions because we were given an equation and we were told to plug in different x values and get an answer. Well, when you work with an equation, that's kind of easy enough. Okay, how do we evaluate functions when we don't have an equation, but we just have a graph to look at? Okay, so just hopefully our previous work up here is going to make this easy. When it asks me, if it presents me with a graph of f, and it asks me, what is f of 0? We have to know that this notation means this is our x value, and what's the y that belongs to x equals 0. We just go to x is 0, we look up or down. Oh, when I look down, oh, my point is here at -3. So when x is 0, y, or the output, the range is -3. And again, a reminder that I can convert in and out of ordered pair form and function notation. Remember, this means 0, -3 is a point on that graph. And it is. All right, what about graph G? What's G of 4? This is the x value. So start at the origin, move to where x is 4, look up, look down. Oh, wait, look up. That's where the graph is. Okay, and kind of eyeball it here. What's the y coordinate when x is 4 here? We'll kind of slide your eyes over here to the left, read from the y-axis. I want to say the height is 4. The y value is 4. This is function notation, and it means that the ordered pair 4, 4 is on the graph of G. Last problem. What's h of -1? When x is -1, I look up. I'm going to say that when x is -1, the height, the y value that I read from over here is 3. So that means -1, 3 is a point that's on the h graph. And just as a reminder, if you need more help with the set builder and interval notation, that will be found in a different video.